In this presentation, I am going to explain the previous GATE questions and answers for the year 2020, and the topic covered is electrical machines. Now let us see the 2020 GATE question. A single 50 Hz synchronous generator on load control was delivering 100 megawatt power in a system. Due to increasing load, generator power had to be increased by 10 megawatt. Therefore, the power is increasing from 100 megawatt to 110 megawatt. As a result of which the system frequency is dropping to 49.75 Hz. Previously it was 50 Hz. When the load becomes 110 megawatt, the frequency equal to 49.75 Hz. Further increasing the load in the system resulted in a frequency of 49.25 Hz. That is, further increasing load, the frequency is reduced to 49.25 Hz. At this condition, the power in megawatt supplied by the generator is round off to the two decimal places. For under this condition, what is the power supplied by the generator? That is the question. Now coming to this one, the variation of the power supplied by the generator versus the frequency, it is a straight line with a negative slope. Therefore, the plot is given here. Therefore, this is the corresponding to 50 Hz, the power supplied equal to 100 megawatt, and corresponding to 49.75 Hz, the corresponding supplied equal to 110 megawatt. And the variation is a straight line with a negative slope. Therefore, P1 equal to 100 megawatt, corresponding frequency equal to 50 Hz, and P2 equal to 100 plus 10, 110 megawatt, corresponding frequency equal to 49.75 Hz. And the variation of the power with respect to the frequency is a straight line with a negative slope. And the equation equal to y equal to mx plus c straight line equation, or correspondingly the y-axis is the power axis, P equal to m into x-axis is the frequency, m into f plus c. Therefore, this is a straight line equation, and we have to find out what is the slope m and what is the y-intercept c. The corresponding to the slope m, we can see that one here, corresponding to 110 megawatt, the frequency equal to 49.75, and corresponding to 100 megawatt, frequency equal to 50. For substituting that one, 110 minus 100, that is divided by 49.75 minus 50, that is the slope of this line, equal to minus 10 divided by 0.25, or minus 40 megawatt per hertz. That is the slope of this straight line. And then next step is we have to find out what is the y-intercept c. To find the y-intercept, already we know that corresponding to 50 hertz, the power delivered or power supplied equal to 100 megawatt. Substituting that equation, P equal to 100 megawatt, which is equal to minus 40 into 50 hertz, that is this point, plus C, or C equal to 2000 plus 100, or that is equal to 2100. So substituting the value of the C as well as M in this equation, we can find out the power for any frequency. Therefore, the question is that for the frequency drop of 49.25 Hz, what is the power delivered? Therefore, substituting that frequency 49.25 in this equation, here P equal to minus M, that's M equal to minus 40. Minus 40 into 49.25 plus C, 2100, which is equal to 130 megawatt. Therefore, the corresponding frequency drop of 49.25 Hz, this point, the power delivered is equal to 130 megawatt. Therefore, that is the answer, 130 megawatt. Now, let us see another problem, 2020 GATE question. A 3-phase 50 Hz 4-pole induction motor runs at a no load with a slip of 1%. With full load, the slip increases to 5%. The percentage speed regulation of the motor round off to the two decimal places. That's the question. Now, 3-phase induction motor, the number of poles 4, frequency equal to F equal to 50 Hz. First step is we have to find out what is the synchronous speed. Ns equal to 120 F by P, or 120 into 50 divided by 4, which is equal to 1500 RPM. Therefore, the synchronous speed of the motor equal to 1500 RPM. Next step is that corresponding to a no load slip of 1%, what is the motor speed? For no load slip equal to 1%, that can be defined as Ns minus N no load divided by Ns into 100, or that is equal to 1%. So 1500 minus no load speed N NL divided by 1500 into 100 equal to 1. Or from this equation, the no load speed is equal to 1485 RPM. Second, full load slip is given as 5%. That is full load slip equal to 5%. Substituting that one, 5% equal to NS minus N full load divided by NS into 100. Or 5 equal, or that's equal to 5. Or 1500 minus full load speed NFL divided by 1500 into 100 equal to 5. Or in this unknown is full load speed NFL, which is equal to 1425 RPM. Therefore, as the motor is loaded, the speed is reducing from 1485 RPM to 1425 RPM. How much is the reduction in speed? That is N at no load minus N at full load divided by related to the full load speed N full load into 100. That is called the speed regulation. Therefore, N at no load equal to 1485 minus N at full load equal to 1425 divided by related to the full load speed 1425 into 100, which is equal to 60 divided by 1425 into 100, which is equal to 4.21%. Therefore, the answer is 4.21%. Let us see another problem, 2020 gate question. A three-phase cylindrical rotor synchronous generator has a synchronous reactance of excess and negligible armature resistance. The magnitude of per phase terminal voltage VA and the magnitude of per phase induced EMF equal to EA. Considering the following, the two statements P and Q, the statement P is for any three-phase balanced leading load connected across the terminals of the synchronous generator, the terminal voltage VA is always more than EA. Second statement Q for any three-phase balanced lagging load connected across the terminals of the synchronous generator, VA is always less than EA. Therefore, these are the statement P and Q. The options are option A, P is true and Q is false. Option B, P is true and Q is true. Option C, P is false and Q is false. Option D, P is false and Q is true. Therefore, these are four options and we will be seeing that explanation of the answer. Answer is the option B, P is true and Q is true. Both P and Q are true. We'll be explaining the, you can see the explanation in the coming slide. Coming to the per phase equivalent circuit of the alternator here, this is the terminal voltage VA and this is the induced voltage EA. Since the armature resistance is negligible, only the synchronous reactance, that is excess, is connected. Therefore, this is the single phase equivalent circuit of the alternator. And here the magnitude of per phase terminal voltage equal to VA and the magnitude of induced voltage equal to EA. And here for a lagging power factor load, meaning that the current IA is lagging the VA by a certain angle phi. Suppose IA is lagging the voltage VA by an angle phi. And here always we know that one, the induced voltage EA equal to the vectorial sum of the terminal voltage and drop across the synchronous reactance. The voltage across the synchronous reactance is perpendicular to the current vector, or we can say the current is lagging the voltage by 90 degree. Therefore, to the terminal voltage VA, we are to add this voltage across the reactance, which is perpendicular to the current vector, that is JIAXS, this is 90 degree, that is vectorially added in order to get the induced voltage EA. Therefore, this is the case lagging power factor. In that case, we can say that one, the terminal voltage is less than the induced voltage if the power factor is lagging. And the other case is that when the power factor is leading, the load power factor is leading here, the current phasor is leading the voltage VA by a certain angle phi. Therefore, this is the phasor diagram in which this is the terminal voltage and the voltage across the synchronous reactance is to be added in order to get the induced voltage that is perpendicular to the current vector. Therefore, that is added JIAXS. Therefore, this is the induced voltage EA. In that case, you can see that one for a leading power factor, the terminal voltage VA is more than the induced voltage EA. Therefore, that is clear from the phasor diagrams of the lagging power factor as well as leading power factor, and this is corresponding to the unity power factor. Therefore, from the phasor diagram, it can be concluded that EA is greater than VA for a lagging power factor, meaning another way you can say that one, VA is less than EA for a lagging power factor and EA is less than VA for a, or we can say that VA is more than EA for a leading power factor. Therefore, this case, that is VA is more than EA for a leading power factor. Therefore, in that case, we can say that both the statements P and Q are true. Hence, the correct answer is the option B. Now, let us see another problem, 2020 gate question. A single phase 4 kVA 200 volt / 100 volt 50 Hz transformer with laminated CRGO steel core has rated no load loss for 50 watts. When the high voltage winding is excited with 160 volt 40 Hz sinusoidal AC supply, the no load loss are found to be 320 watts. Second case, when the voltage magnitude 160 and frequency 40 Hz, the loss is reduced from 450 watts to 320 watts. When the high voltage winding of the same transformer is supplied from a 100 volt 25 Hz sinusoidal AC source, the no load loss will be how much? That is rounded off to 2 decimal places. Therefore, corresponding to this condition, the voltage 100 volt and 25 Hertz frequency, what is the no load loss? That is the question. Therefore, coming to this one, the iron loss or no load loss, both are same. Iron loss of the transformer corresponding to the 200 volts and 50 Hertz, which is equal to 450 watts, and V by F equal to 200 divided by 50, which is equal to 4. And the second case, as the voltage is reduced to 160 volt and frequency 40 Hertz, the corresponding loss is equal to 320 watts. And corresponding V by F equal to 160 divided by 40, that's equal to 4. It's very clear that the V by F ratio is same in these two cases. That indicates that flux density or BM is same, or flux conditions are same in the core in these two cases. Now continuing the same problem, 220 gate question. As we have seen, the no load loss is the summation of the eddy current loss and hysteresis loss. Eddy current loss equal to a constant eddy current loss Ke into Bmax square plus into F square T square V. Bmax is the flux density, maximum flux density. F is the frequency, T is the lamination thickness, and V is the volume. In that one, Bmax is constant, Ke is a constant, T is a constant, and V is a constant. Or we can say that another one constant K1 into F square. Therefore, eddy current loss equal to a constant K1 into F square. That's equation 1. Second equation, hysteresis loss is equal to the eta, which is equal to Steinmetz constant, eta into Bmax over 1.6 F into V. Bmax is a constant, V is a constant, eta is a constant. Therefore, another constant K2 into F. Therefore, hysteresis loss PH equal to another constant K2 into F. That's the second equation. Therefore, the total no load loss or iron loss is the summation of these two things, or iron loss equal to eddy current loss plus hysteresis loss, or K1 F square plus K2 into F. That's equation 3. Now, coming to the data given in the problem, corresponding to 50 Hz, the loss is equal to 450 watts. For 450 equal to K1 into 50 square plus K2 into 50, which is equal to 2500 K1 plus 50 K2 equal to 450 watts. Equation 4. Second statement is that corresponding to 40 Hz, the corresponding loss equal to 320 watts. Therefore, K1 into 40 square plus K2 into 40, or 1600 K1 plus 40 K2 equal to 320 watts. Therefore, that's equation 5. Solving this equation 4 and 5, the unknowns K1 and K2 can be obtained. K1 equal to 0.1 and K2 equal to 4. Now the question is that corresponding to 100 volt and 25 Hz, what is the no load loss? Again, V by F, if you calculate 100 divided by 25 equal to 4, the same as the previous cases. Therefore, Bmax is constant. Now coming to the calculation of the no load loss corresponding to 25 Hz, it is equal to K1 into 25 square plus K2 into 25. K1 equal to 0.1 into 25 square plus 4 into 25. It equal to 162.5 watts. Therefore, the answer is that corresponding to 100 volts 25 Hz, the no load loss equal to 162.5 watts. Let us see another problem, that is 2020 gate question. A cylindrical rotor synchronous generator has steady state synchronous reactance of 0.7 per unit and subtransient reactance of 0.2 per unit. It is operating at 1 plus J0 per unit terminal voltage with an internal EMF of 1 plus J0.7 per unit. Following a 3-phase solid short circuit fault at the terminals of the generator, the magnitude of the subtransient internal EMF rounded off to 2 decimal place, that how much per unit. Therefore, this is the equivalent circuit of a synchronous generator. This is the generated voltage 1 plus Eg equal to 1 plus J 0.7 per unit, and the terminal voltage 1 plus J0, and XD equal to J 0.7 per unit, and the subtraction reactance 0.2 J 0.2 per unit. The case 1, before the fault, pre-fault condition, the generator current equal to Eg, that is generator voltage minus terminal voltage, Eg minus Vt divided by XD, or equal to 1 plus J 0.7 minus 1 divided by J 0.7, or 1 angle 0 per unit, or the generator current equal to 1 per unit. That is corresponding to the condition, pre-fault condition. Now continuation of the same problem, case 2, that is post-fault condition. This is a post-fault condition that IF dash is equal to, that this current is equal to this voltage 1 plus J0, 1 angle 0, and this is equal to J 0.2, that is 0.2 angle 90, or equal to 5 angle minus 90, or the total current Ig total equal to Ig plus IF double dash, or that 1 angle 0 plus 5 angle minus 90, summation of that one, or that's equal to 1 minus J 5, or subtraction EMF is given by, it is equal to Ig total into the corresponding reactance, or 1 minus J5 into J 0.2, which is equal to 1 plus J 0.2, or the magnitude of this one, subtraction EMF, equal to square root of 1 square plus 0.2 square, which is equal to 1.02 per unit. Therefore, the answer is 1.02 per unit. Let us see another problem of 220 gate question. The figure below shows the per phase open circuit characteristics measured in voltage and the short circuit characteristics measured in ampere of a 14 kVA 400 volts 50 Hz 4 pole 3 phase delta connected alternator driven at 1500 rpm. Therefore, this is the OCC field current versus the open circuit voltage, open circuit characteristic, and this is a short circuit characteristic, field current versus short circuit current. And the field current IF is measured in amperes. The readings taken are marked in the respective XY coordinate in the figure. Ratio of the unsaturated and the saturated synchronous impedance of the alternator is closest to, what is the ratio of the synchronous impedance in the unsaturated region divided by the synchronous impedance the saturated region. That ratio approximate, or that is the short closest to, which out of these options are A 2.05, B 2, C 2.1, and D 1. Therefore, we'll be seeing in the coming slides. The answer is option C. We'll be seeing the explanation in the coming slide. Now continuing the same problem, 228 question. Here, this is the plot of OCC in which this is the field current and this is open circuit voltage, and this is the short circuit characteristics, field current and short circuit current. Now we have to find out what is the impedance on this region, and similarly what is the impedance on this region, and take the ratio. That is the question. Therefore, coming to that, to find out the impedance, we have to find out the corresponding voltage and short circuit current. Now let us see the short circuit current in this point here. We can, from the short, the writing is 3-phase delta connected alternator, 14 kVA, 400 volt terminal voltage, frequency 50, number of poles equal to 4. And from the short circuit characteristics, that is this one, the field current IF equal to 4 amperes, that is the field current is corresponding to field current 4 amperes. The short circuit current, it is given in the problem, it is as 20 amperes. That is this point. Now we have to extrapolate corresponding to field current of 2 amperes as well as field current of 4 amperes. What is the short circuit? Because this is a straight line equation. Therefore, from that one, for a field current of 2 amperes, that is for a field current of 2 amperes, we can see that one from this equation, the slope is given by, it is equal to, we see the slope of that one is given by here 20 divided by 4. 5 is the slope of this line. Therefore, here if you see corresponding to 2 amperes, 20 divided by 4, 5. For 2 into 5, that is 10 ampere, corresponding to field current ampere to current, that's equal to 10 ampere is the short circuit current. Similarly, corresponding to a field current of say that is corresponding to 8 amperes, that is field current of 8 amperes, the corresponding the field current of 8 amperes, the short circuit current equal to 8 into 5, 40 amperes. That is, this is a straight line. This is a straight line. Therefore, that can be extrapolated or that can be calculated. Therefore, from now we have to find out what is the impedance in this region, and for that one, the unsaturated region impedance set unsaturated is given by corresponding to 2 ampere field current. The open circuit voltage is given by 210 volt, and corresponding short circuit current we calculate it is equal to 10 amperes. Therefore, it is equal to 210 volt and 10 ampere is the short circuit current, and this is the open circuit voltage. Therefore, the unsaturated region impedance equal to synchronous impedance equal to 210 volt divided by 10 ampere with 21 ohm. Therefore, the impedance in this region equal to 21 ohm. Now, in this region, to find out that one, the open circuit voltage that is equal to, we can see that one open circuit voltage equal to 400 volts, and corresponding short circuit current we calculated all corresponding to 8 ampere field current, short circuit current equal to 40 amperes. Therefore, short circuit current equal to 40 amperes. Therefore, 400 volts divided by 40 amperes, that is the synchronous impedance in the saturated region. Therefore, Z saturated equal to 400 divided by 40 equal to 10 ohms. Therefore, the synchronous impedance in the unsaturated region equal to 21 ohm, and the synchronous impedance in the saturated region equal to 10 ohm. Now the question is that what is the ratio of the synchronous impedance of unsaturated to the synchronous impedance of the saturated? Set unsaturated divided by set saturated is given by 21 divided by 10 is equal to 2.1. Therefore, the answers are here: A 2.05, B 2.0, C 2.1, and D 1. Therefore, the answer is the option C, which is equal to 2.1. Now let's see another problem, 2020 gate question. A 250 volt DC shunt motor has an armature resistance of 0.2 ohm and the field resistance of 100 ohm. When the motor is operated on no load at rated voltage, it draws an armature current of 5 amperes and runs at 1200 rpm. When the load is coupled to the motor, if it draws a total current of 50 amperes at the rated voltage. Therefore, under loaded condition, it is taking the total line current equal to 50 amperes, and with a 5% reduction in the air gap flux due to the armature reaction. Voltage drop across the brushes can be 1 volt per brush under all operating condition. The speed of the motor in RPM under loaded condition, that is, it is closest to how much is the speed of the motor under loaded condition. That's the question. Therefore, this is it is a DC shunt motor, and in which the shunt resistance is given as 100 ohm. The supply voltage, DC supply voltage is 250 volt. Therefore, the shunt field current equal to 250 divided by 100 or 2.5 amperes. And here, in this case, let us see the options are the speed of this one: option A 900, option B 1200, option C 1000, and option D 1220 rpm. Now, coming to the DC motor circuit here, the input voltage equal to 250 and the armature resistance RA equal to 0.2 ohm and the field resistance RSH is equal to 100 ohm, and no load current, that is under no load condition, the no load current armature current is given as IA no load equal to 5 amperes, and the no load speed NL equal to 1200, that is given in the problem 1200 rpm under no load condition. And the brush drop is given as, it is given per brush 1 volt. Since there are 2 brushes, 2 into 1, total brush drop will be 2 volts. And 1 volt per brush. And the back EMF corresponding to the no load condition is equal to the terminal voltage plus the drop across the armature resistance and the brush drop. Therefore, terminal voltage is the back EMF equal to the terminal voltage minus the drop. In a motor, the back EMF is equal to the applied voltage minus the drop across the armature and the brush drop, or V minus IA at no load into RA minus 2 into the brush drop VB. For substituting that one, 250 is the terminal voltage, applied voltage, minus drop across the armature equal to 5 into 0.2 minus the brush drop equal to 2 into 1. or 247 volt is the back EMF corresponding to the no load condition. Now let us see the loaded condition in the coming slide. Now continue with the same problem here. Under loaded condition, that is when this is loaded here, the line current is given as 50 amperes. This is given as 50 amperes. And the shunt field current can be calculated as 250 divided by 100 or 2.5 amperes. Therefore, the corresponding armature current equal to the line current 50 minus the shunt field current, or 50 minus 250 divided by 100, or 47.5 ampere is the IA at full load. Therefore, IA at full load or IA at loaded condition, IAL equal to 47.5 amperes. Therefore, here the corresponding back EMF equal to the terminal voltage minus the drop across the armature and the brush drop. Therefore, V, which is equal to 250 minus armature current calculated as 47.5 into armature resistance equal to 0.2 ohm into 0.2 minus brush drop equal to 2 into 1 or 238.5 volt. Therefore, the back EMF under loaded condition is equal to 238.5. Now, as the motor is loaded, due to the armature reaction, flux is reducing. How that is given, that is the second case, that is here at no load condition. This is a flux at loaded condition. This is a flux under no load condition. Flux at loaded condition is 95% or 0.95 times of the flux at no load condition. Now, the basic relation between the speed of the motor, back EMF and the flux is given by N at no load is proportional to EB at no load divided by phi at no load. And the N at load is proportional to EB at load divided by phi at load. And from this equation, we can say that the speed at load divided by speed at no load equal to the back EMF at load divided by back EMF at no load into the flux at no load divided by flux at loaded condition. Then here, this we already calculated. What is the flux at loaded equal to 238.5 and flux at no load condition 247 into this ratio. This is the ratio because of the armature reaction. There is a reduction, that is phi at no load divided by phi at load, 1 by 0.95, 5% reduction due to the armature reaction. Therefore, in that case 1 by 0.95, and here we can calculate the speed at loaded condition equal to into the speed at no load condition, that is multiplied here, that is this equation. We are multiplying that one. Full load speed at loaded condition equal to this equation is used to find out the speed at loaded condition into 1200, which is the no load speed multiplied. Then we'll be getting 1219.69, or that can be approximated to 1220 RPM. Therefore, the answer is here 900 RPM, option A, B 1200 RPM, C 1000 RPM, and D equal to 1220. Therefore, the answer here is that option option 1220 RPM. Therefore, the option D is the answer. Meaning that at loaded condition, the speed of the motor is 1220. Let us see another problem, 2020 gate question. A cylindrical rotor synchronous generator with a constant real power output and constant terminal voltage is supplying 100 amperes current at 0.9 power factor, lagging power factor. An ideal reactor is now connected in parallel with the load, as a result of which the total lagging reactive power requirement of the load is twice the previous value, while the real power terminal remains same. Real power remaining unchanged. And the armature current is now, in the second case, when a reactor is connected, what is the corresponding armature current? Previously it was 100 amperes. Now when a reactor is connected, that is supplying total twice the reactive power. Then what is the current? That is round off to 2 decimal places. Now this is the phasor diagram. Let us see the cylindrical rotor synchronous generator. And the first case, it is 100 amperes and the power factor equal to this one, cos phi 1, which is equal to 0.9 lagging. This is the corresponding the phasor diagram as such. Therefore, the corresponding phase angle equal to 0.9 lagging corresponding phase angle equal to 25.84 degrees. And the reactive power, corresponding reactive power equal to this one. This is the reactive power corresponding to the first case, that is 0.9 lag per factor load. That is happening. Therefore, the real power is equal to P1. This is the real power and this is the reactive power and this is a power factor angle which is equal to 25.84 degrees. That's the first case before connecting the reactor. Now, after connecting the reactor, let us see. We can see in the next slide. Now, continuing the same problem, 2020 gate question. As connecting reactor in parallel with the load, when you are connecting a reactor parallel with the load, let the reactive power be equal to Q2. That is, the total power is equal to Q2. This is the total power, reactive power equal to Q2 when a reactor is connected. But the real power is same. You can say that real power is same. Now, it gives that the real power is P2 equal to, since the total real power requirement is same, we can say that this P2 equal to P1, or there is no change in the real power requirement. That is same. But the reactive power requirement is increased. Previous value just double that one actually. Therefore, it is given that the second case that total reactive power equal to 2 times the Q1. This is Q1 and the total is equal to 2 times Q1. Now, this is equal to the second case that power factor angle equal to phi 2, or you can say that tan phi 2 equal to this one Q2 divided by P2 or P1, both are same. Q2 divided by P2 which is equal to Q2 divided by P1, or Q2 is equal to 2 times Q1. Already we have seen that the reactive power supplied when a reactor is 2 times the reactive power without reactor. Therefore, that is equal to 2 times Q1 divided by P1, or 2 times Q1 by P1 is already we have seen it is equal to tan phi 1. Therefore, 2 times tan phi 1, or it is equal to 2 times tan 25.84 degrees, or which is equal to 0.9686, or this is equal to cos phi 2 equal to, we can see that one cos power factor is equal to cos here. Okay, it is corresponding, we can say cos 44.086 or 0.7185 lagging. Therefore, here the cos phi 2, that is this one, the total power factor is now reduced to 0.7185 lagging after connecting the reactor. Now, since the power factor is reduced, of course, the current will be increasing. Now, how much is the current drawn? Total current when you are connecting a reactor parallel to the load, how much is that current drawn? So to find out that one, since we can say that one I1 cos phi n equal to same as I2 cos phi 2. I1 cos phi n equal to I2 cos phi 2, or mean that the real power is same. That is why I1 cos phi 1 equal to I2 cos phi 2, or I2 equal to, we can say that one I1 cos phi 1 divided by cos phi 2, or first case without connecting reactor 100 ampere is there. For 100 into cos phi 1 equal to given as 0.9 and cos phi 2 equal to 0.7185, or that is equal to 125.26 amperes. Therefore, when we are connecting a reactor parallel to the load, the current is increasing from 100 amperes to 125.26 amperes. Therefore, the correct answer is 125.26 amperes.